I'm talking about merchant silicon, or how I call it, fun with ASICs. I want to start by giving you an overview from 2022 about the prediction of the speeds on the market. It's not accurate right now because of COVID. We had the lead time issues. So the technology shift was by 2 years. So we expect, for example, 1.6 terabit by 2026, so next year, and not like 24, how Del Oro was predicting it like 2 years ago. But what's still true is that we expect by 26 that 45% of the market are 800G or higher, right? And the rest will be 400G and below. So given that, what is necessary to fulfill such kind of speeds? And the limiting factor is SerDes speed. SerDes is basically the electrical interface which goes from the ASIC to the front panel port. And that's the limiting factor, to be honest. But if we take a look about merchant silicon, I want to basically explain what does merchant silicon mean. Merchant silicon is just ASICs you buy from someone everyone can buy from, like Broadcom in our case. There is merchant silicon and custom or proprietary silicon, which means it's homegrown ASICs, which some vendors use and some use the other stuff. Technically, there is a difference between RTC, so run to completion-based ASICs. Those are the ASICs where you have like hundreds of NPUs, and you can concatenate those NPUs. Like you have VLAN decapsulation, some lookup, some counting, and so on and so on. Those RTC-based ASICs have some advantages because they're pretty flexible. You can, concatenate every NPU with each other and do whatever you want. The disadvantage is they're pretty complex from a kind of pipeline perspective, which means they need a lot more power. The other ASICs are pipeline-based ASICs, so that's the stuff we're going to talk about today. Pipeline just means, as the name says, it's like a fixed way the packet can take inside the ASIC, right? Of course, we have recirculation channels, which means that if I need to cycle the packet again inside the chip, we can do that. So, for example, if you need to have a double lookup or double NCAP or whatever, we can do that, but the pipeline is basically designed when designing the ASIC, and you can't change it because it's like a fixed pipeline. Advantage is it's much simpler because the pipeline is fixed. You save power. Disadvantage is it's not that flexible. Yeah, but what I want to show you today, it's like good enough for many use cases. And this presentation is not marketing bullshit. It just should give you an overview what is what and what is the best ASIC for which use case in your network, right? So if we take a look, and that's always fascinating because in 2008 we had the first 24-port 10G switch or chip, a single chip. If we take a look to 2022, we had the first 128-port 400G single chip. So it's quite an evolution, right, from 2410 to 128 400G. And we already have 800G chips, which we are shipping. And our Andy Berchtesgaden, it's like our chief development officer, he's already developing 1.6 terabit currently, which we expect in kind of next year, in the next 1 to 2 years. And what is key to designing kind of those SerDes speeds or to get those speeds up? Well, first of all, the serializer or deserializer, short SerDes, is the technology we use to connect the chip to the front panel port, or to be more precise, to the DSP of the optics, right? So the SerDes speed is basically limiting our bandwidth because it has like 10G, 25G, 50G technology, or currently 100G. So the next SerDes step will be 200G. And when I have 50G SerDes, it means I need 2 lanes to achieve 100G, because 2 times 50 is 100. If I have 100G based SerDes, I need 1 lane to do the same, right? So I need half of the lanes to do the same, which basically means I can double my bandwidth if I have the same amount of SerDes links. And there is like one saying of our Andy Berchtesgaden, which is the easiest way to go faster is just to go faster, right? It sounds logical, it sounds simple, it's not, but I will basically tell you more about that later. I don't want to bore you with all the details about SerDes and how the bits are going. Another component of ASICs is not only the SerDes speeds, the kind of throughput, it's buffers, right? And there are different ASICs having different buffers. So now the question is, are more buffer better or worse? And the answer is, it depends. It just depends on what you want to do, right? So when do we need buffers in networks? It's like the incast use case, like I have many interfaces going to one or two upstream interfaces. Or the other way around, which is even worse, which is like the speed change. When I come from 400G interfaces and I need to go to 10G, right, the transmission is simply slower. It's not only that the bandwidth is less, the transmission, the signaling, the kind of sending, placing bits on the SerDes is just simply slower, so I need to store it, right? And that's when buffer matters. There are some other use cases as well, like storage networks. Like storage tend to have like the attitude, if I have 100G interfaces, I use 100G. So you need to cope with that in the networks. But typically, if I talk data center, if I have my compute stuff, I don't need that much buffers. So if we take a look about where merchant silicon were fitting in 2008, we were talking about the leaf use case. In 12, we had SPI and leaf, so basically we were able to fulfill data center use cases, and now basically merchant silicon can do from optical transport, routing, switching, whatever you need. There are some stuff which you can't do compared to custom silicon, but you always need to see what are the advantages and disadvantages for my use case. So if we talk about processing, of course, the manufacturing form factor matters, because if I produce in 7 nanometers, I have my transistors. If I produce in 3 nanometers, I can place basically more than double the transistors on the chip, which means I have more bandwidth, more throughput, but at the same time, I use less power, right? So kind of the power per bit is decreasing in total. And that's basically why every process generation enables us to give you more throughput, better power efficiency, more buffers, and bigger scale, bigger routing tables, max scale, whatever, because we can put more transistors basically in less space. So now, why should you as a customer or as a network operator care about the ASIC itself? Because most people buy boxes based on data sheets, on features, on scale. Why basically thinking about the silicon? Well, first of all, we don't produce that kind of chips. Like every vendor buys it from, in that case, Broadcom or any other kind of merchant silicon manufacturer, but Broadcom had basically made hold of most of the other guys. So there is Broadcom, and then there are some minor players in the market. If we look at the cost of producing a chip, right? So if we look, for example, at 5 nanometers, we are about $450 million just for designing the chip, for developing it, for testing it, until I can ship it. That's insane, right? So the problem is what we see with proprietary ASICs, that vendors try to get rid of them and sell them as long as they can. We don't need to do that, or other vendors don't need to do that if we have merchant, because that cost is carried by Broadcom, not by us, right? So we just say we need that kind of quantity of this ASIC, that quantity of that ASIC, ship it to us, and we build our products, and that's it. So it's basically cheaper, it's consuming less power, and that gives you faster innovation cycles, right? So you see that always Broadcom is first in producing 400G, 800G, and they will be first, I'm pretty sure, with 1.6 tera chips, because for them it's easier. They produce it, some other guys sell it. Right? You don't have all the costs in-house. So what is now better, right? Custom silicon, merchant silicon? Well, the answer is it depends. I can't answer it for you, right? So basically, everyone has access to the same technologies, right? We have the same fabrication lines, we have the same memories, the same SerDes technology, right? We don't do some magic tricks, right? It's all the same. It's just like you have disadvantages and advantages with each approach, and you need to assess what is better for my use case, right? So, well, why we stick with merchant silicon is faster innovation cycles, right? We need these products because the cloud guys, the hyperscalers, are pushing us every year. We need 800 gig. Okay, now we have 800 gig. We need 1.6 tera. We need double the capacity, but half the price per bit, right? So that's only possible with that kind of silicon. I skipped that slide. So when we talk about silicon, about merchant silicon, what kind of groups or families do we have currently? So basically, we have the Tofino, which is not from Broadcom. It's made by Intel. The chip is, when you buy it, it's basically dumb. It doesn't know anything. You need to program it, like you need to learn it how an Ethernet frame looks like, how to process an Ethernet frame. But the advantage is it's absolutely flexible. You can do whatever you want with that when coding it. There is the Tomahawk family, which is like, I call it the packet accelerator. It's packet in, packet out. That's basically what it's designed to do. Trident is more for the compute data center use case, campus use case, right? You have decent buffers, you have many features, and Jericho is more the routing kind of chip in that family, like high-scale routing, deep buffers, a more flexible pipeline. The problem is the Tofino was killed by Broadcom, by Intel, sorry, because they basically stopped the roadmap. Right? So you can still buy the Tofino chips, but they basically said we won't develop it any further, so you can buy it, you can do whatever you want, but there is no roadmap, and yeah, we don't know what we will do in the future. Which means for customers at the end, you have now those three families, because going with something which has no roadmap might be fine, but for many customers it might not be suitable if you don't have like future bandwidth speeds. I briefly want to cover the different ASICs so that you can basically make your decision what to get. So the Tomahawk 5, it was initially designed for AI networks, because AI networks tend to have high bandwidth requirements, low latency requirements, special load balancing requirements. So that was the first chip with 100G SerDes, PAM4 SerDes speeds, and it's a 50 tera kind of chip. It has like decent features. You have VXLAN, you have some load balancing features. It has like a big radix. You have up to 320 front panel ports from 10 to 800G. And that's basically the ASICs we use for AI networks or cloud networks. So I'm not going through the table, don't worry, it's just for your reference. If we look at the Trident, it has more buffers than the Tomahawk, right? So it's more feature-rich, has a more complex pipeline, more buffers, and that enables this chip to be present in campus networks, data center networks, so VXLAN, EVPN, everything basically you want to do in the data center, that's the chip you want to go. It's available in two form factors, like the Trident 4, the latest generation, 12 tera or 8 tera, depending on what kind of front panel ports you want to have. And those chips give you basically let me call it like the standard feature set you need in modern networks. It has up to 40% less power consumption than the previous generation. But be careful, if you read the data sheets, the value will be higher because it's like power per bit. Of course, you get more bit, you have more power, but if you calculate it, the relation, it will be lower. And the last stuff I want to mention, to not go over my time, are the Jericho ASICs. So Jericho is something special because it has high amount of buffers. What does it mean? Like, for example, the Trident family, it has around like 100 megabit. The Jericho starts at 2 gigabit, right? So it's quite a jump. Why do we need it? Maybe if you're running a service provider network, you have 1G, 10G access, but 100G or 400G uplink interfaces, you don't want to lose packets, right? I mean, the customer won't accept the fact that you say, oh, well, we transition from 400G to 1G. You have to accept packet drops. Yeah, customer won't accept the packet drops, so you need to have decent buffer, also if you want to do shaping, policing, etc. It has 50G service. I will talk about the next generation, which comes this year in a minute. It's like 7 terabit, but it has a very flexible pipeline. So you see the diagram looks much more complicated than the one before. Because here we can do much more complex features which are used by internet exchanges or service providers, like hairpinning, sub-interfaces, doing some VLAN manipulation, all that stuff. Of course, it has more power consumption because the pipeline is more complex, but it has basically a different use case than the others. I'm not going through the table again, it's just for your reference. It should just point out that with the latest series, we can do up to 4 million routes in hardware. So that's the FIP capacity, which is basically suitable for modern peering use cases or P use cases. So what's the roadmap? It's Jericho 3. Be careful. There is already a Jericho 3 AI out. That's an AI-optimized chip. It has only the features used for AI networks, so you can't use it in a service provider network. The full J3 will come later this year. It's the first Jericho with 100G. And the Tomahawk 5 and the Jericho 3 have high power SerDes interfaces, which can enable linear drive optics. I will talk about that in a minute. Be careful, because that's something I get often asked. Like, can I do 1G? Well, if you buy a 400 or 800G box, I wouldn't assume that on the same ports you can do 1G, because that's quite a different kind of speed. So the SerDes interfaces don't allow that. So there are basically 2 options. That's on us, using gearboxes to transition the speed. But be aware that the Jericho chips don't support auto-negotiation. Because of the different SerDes technologies, they don't. If you want to do it, there are special rate-adapting transceivers, which are basically 10G internally and 1G to the external world, and they support auto-negotiation. So last thing, linear drive optics, what does it mean? And why should we think about it? The high-level summary is, like the guys from Flex Optics told you, there is a DSP chip on each optics, the digital signal processor. That's where all the magic happens. The problem is, that's where all the power is needed, right? So what we did, especially for AI networks, because the GPU clusters need up to 2 kilowatts per GPU unit, so that's quite a massive amount of energy, so we need to save it in the network. So what we did is we used the DSP, or we removed the DSP from the optic, and we place it basically in the chip, in the ASIC itself. So the optic is more now the conversion stuff, but all the signal processing happens in the ASIC. That's only possible because those new chips have like the high power ASIC, high power SerDes speeds, and that cuts power by up to 50% on the optic side, right? So if you have the ZR plus optics up to 20 watts, if you have like a chassis with 50 basically optics, you can calculate it yourself. So it's quite an amount of power which we save. So concluding, how does that basically transform it, and why is it basically transformed? The boost in AI networking is also boosting the other industries, because we use basically the same chips. And the AI networking requirements are very different. Those are insane, because the GPU says, I have an 800G interface, I will use 800G when I want to use it, right? So it's not like constantly, it's just like penetrating the network whenever it does some calculations. And to cope with that, of course, we need to adapt those ASICs. And all of those changes, the processing changes, all the power savings are, of course, also available to other markets, like, for example, service provider networks, because those are the same chips. So with that, and I think a little bit over, I'm sorry, I'm done with my presentation. yeah, if you want to ask questions, you can also reach me outside to save some time. And I say thank you for having me.
Thank you very much.